Hello everyone, welcome to part 2 of the multi-part series on mathematics behind principal component analysis. In this video, I'm going to spend significant time talking on three important topics: covariance, variance, and of course, correlation. I strongly believe you need to have a solid understanding of these three topics as part of the mathematics behind principal component analysis itself. If you understand these topics well, you'll be well poised to take advantage of applying principal component analysis in an unsupervised setting for dimension reduction techniques. Without much ado, let's get started. Hope you're all excited. If so, please watch this video till the end for maximum benefit. Let's get started with covariance. I think first it's important to define covariance. So some of you may be familiar, and therefore I'm going to quickly drive our attention to what is this covariance. Let me select the pen here for writing and explaining in a little more intuitive fashion. Probably I'll take this color. Hopefully you should be able to see at the other side legible. So covariance basically gives you the direction. Okay, direction in which, let's say, two random variables or two quantities vary with each other. Okay, so that's what covariance means. Two quantities vary with each other. So here is a pertinent question to ask. Do you think covariance gives you the magnitude of variation? So what do you think? Please let me know in the comment section. Let's understand in greater detail, what is it actually trying to tell when I say direction in which two quantities vary with each other? What is it actually telling? What is it even measuring? Covariance actually measures, let's just add that as another point because it's important, measures the joint variation or the joint dispersion of two variables. Dispersion of two variables. To be specific, two random variables, but I'm going to call it as two variables. Okay, that's more detailed explanation of what covariance measures. So covariance is a measure of the joint variation or joint dispersion of two variables. So I think it's not enough if I tell you this. We need to talk about the formula, and we need to look at the pictorial representation of what is this covariance I'm talking about. So let's go to the next slide. And first, let me just draw a diagram to show how does it look. Let us say we have two variables taken x and y. We are after all talking about the joint dispersion of the joint variance. So we will have data points like this. You can think of data points to be like this. Okay, you can think of data points to be like this. So let us say I'm going to put a filled circle here, and this point is the representation of x bar, y bar. So I can drop a line perpendicular to x-axis, and this is where it meets the x-axis, and I can drop a line perpendicular to the y-axis where it meets the y-axis. I can extend these lines if we want. Okay, so this is your x bar, y bar, the average representation of two variables, x bar, y bar, for x and y variables respectively. So I can think of the variation to be, I'm going to putting it in a solid oval shape. Around this mean, how is the dispersion? We can think of like this. We can also look at the dispersion around the mean to be like this. Okay, if we look at the joint dispersional variation of these two variables with respect to the mean that we are looking at here, which is represented as x bar, y bar, is what we are talking about covariance in general. Okay, so how does the formula look like? So let's call this as covariance of x comma y. I'm going to write down the formula first, and I'm going to explain every bit of it. 1 upon n minus 1 summation I running from 1 to n xi minus x bar multiplied by yi minus y bar. Okay, there is a subtle difference in the formula when you are looking at for an underlying population, and that is therefore instead of n minus 1 you will have n. For example, we use typically n minus 1. So covariance of x and y, that is covariance between two random variables x and y, is defined and represented mathematically as 1 upon n minus 1 summation I running from 1 to n xi minus x bar multiplied by yi minus y bar, where this n you can think of as the number of subjects. So n is the number of subjects. You can also think of these subjects as number of rows in a matrix. For example, if you have 10 rows in a matrix or 10 records in a data set, you can think of them to be n is equal to 10. So 10 rows in a matrix or 10 records in a data set. That's what it is. Okay, so xi running from 1 to n, let us say you have 10 subjects or 10 rows. So each value of I would take anywhere between 1 to 10, xi, x1, x2, x3, etc. all the way up to x10. Similarly for yi, taking values of y1, y2, etc. all the way up to y10 if you have n is equal to 10. That's what this summation I is equal to 1 to n. Okay. Small change for the population is divided by n instead of n minus 1. So this is the covariance. Okay. Hope this is amply clear as to what covariance is. So moving on, I'll just make subtle difference to this and then talk about variance. So let us take a case of variance. So what do you think, given what I explained about covariance, any thoughts on what you think the variance would be? Probably I can pause for a few seconds for you to absorb and then think about it. Okay. So let us take the formula for covariance. I'm just going to quickly repeat. 1 upon n minus 1 summation I running from 1 to n xi minus x bar multiplied by yi minus y bar. So this is covariance. Okay. So notice here covariance of xy is same as covariance of yx. I'll just show this when I'm talking about the demo little later in the video. Okay, so covariance of xy is same as covariance of yx. Covariance of yz is same as covariance of zx, etc. I'm going to simply do some modification to this covariance formula to look at variance. So before that, I think we will have to understand what is this variance. Okay, so variance basically tells us how much a quantity varies with respect to its mean. So it tells us what? How much a variable or a quantity varies with respect to its mean. Okay, that's what basically variance is. That essentially means how far away from the mean is what variance is all about. Okay, if I can further simplify that, let's derive the formula for variance. I'm going to do a small change. I'm going to replace y with x in this formula. What happens? So I'm going to talk about covariance of x against itself. So what will be the change in the formula? 1 upon n minus 1 I running from 1 to n xi minus x bar would remain the same. Instead of yi and y bar, I'm going to replace with x with y, and therefore it will become xi minus x bar. So what is this? Xi minus xi bar multiplied by xi minus xi bar is nothing but, I'll write it here or I can write it in the next line also. So I'm going to quickly transition to next slide and then put it 1 upon n minus 1 I running from 1 to n xi minus x bar the whole square. So what is this term? Many of you would recognize, make no mistake about it, this is the definition of variance, isn't it? It's the definition of variance. Many of you would be comfortable with this, right? You have come across this before. So this is a more generalized variance. Okay. So the covariance of a variable against itself is nothing but variance of the variable x. If we are talking about covariance of x with x, covariance of x with x is nothing but the variance of the variable x. So this variance tells you what? Is a measure of how far a particular observation is away from the mean or how far it is from its mean. So covariance of a variable against itself is the same as variance of x. Why? This is formally if you look at xi minus xy. So there is nothing to memorize here, friends. So you can remember one possibly, or by practice it becomes muscle memory. From the one you can derive the other. Okay. So this variance tells you how far an observation is away from the mean. Okay. So here are one or two questions that I'm going to ask. Can covariance be negative? Can variance be negative? Please let me know in the comments what do you think. Okay. Notice here, I'm going to take covariance of variable against itself. So it's the single variable x. So covariance of variable against itself is nothing but the variance of x. When you look at variance of x, we have one dimension or one variable. Whereas when you look at covariance, we are having two variables. So covariance is always between variables or a measure of joint dispersion of two variables. When you talk about the variance of a particular variable, you're talking about one dimension only of that variable. That's a distinction that I want you to clearly remember. Okay. So I think we can transition to idea of correlation. Here is what I'm going to conclude for covariance and variance for now. Okay. So you need to be having a clear understanding of what variance of a variable is, and therefore what does covariance measure or covariance represent, so that you will make these ideas and take it to the world of principal component analysis along with what we discussed in part 1 of the video. And by the way, if you have not already watched part 1, I strongly recommend for you to not to miss watching that. There is a wealth of content shared by me from the practitioner's perspective for maths behind principal component analysis. And I therefore request you to watch that video and watch this, because these two should go together, to my understanding. Okay. So correlation is the last topic that I want to discuss. Probably I'm going to go to the next slide and put the title as correlation. So what is correlation? Very familiar for some of you, right? So correlation is a measure of not just the direction, but the strength of the relationship. Okay. Like for example, if you take advertisement expenditure and sales, you would know both of them are positively correlated. That essentially means as and when advertisement expenditure goes up, sales more likely to go up. That's a positive correlation. Okay. If I can represent this as correlation between advertisement expenditure and sales as, let us say, 0.65, so it is a positive quantity and tells you the correlation in terms of the direction and the magnitude or the strength of the relationship. This is positive. So correlation values would be strictly between -1 and +1, where we talk about -1 to be strongly negatively correlated, +1 to be strongly positively correlated, and every other value between -1 and +1 to be moderately high negative to moderately negative to low negative to high positive, moderately high positive, extremely positive, or strongly positive, whatever. So those are the interpretations. So this is worth noting. So I mentioned at the beginning of the video, the idea of covariance is used for computing correlation. So what is it? So I'm going to take covariance one more time so that you will be crystal about what I'm talking. How did we define mathematically? 1 upon n minus 1. I running from 1 to n. Xi minus x bar multiplied by yi minus y bar. I'm going to draw a line not to mix up things. So this is covariance. Okay. So I can divide this covariance. When I say covariance, replace this with entire this side of the equal to sign, right hand side of equal to. When I divide covariance by standard deviation of x multiplied by standard deviation of y, no points for guessing, this, my friends, is called correlation. This is called correlation. Okay. In doing so, you can come up with yet another definition for correlation, not just in terms of the measure of the relationships, if we examine this, when I take covariance or this whole thing that I've written here, divide it by standard deviation of the two variables x and y respectively as a product of standard deviation of the two variables, this expression becomes dimensionless. Dimensionless. So one other definition you can think of for correlation is the dimensionless version of covariance. Okay, simply put, let me repeat for thoroughness. Correlation is a dimensionless version of covariance. So therefore, covariance is used to compute correlation. Okay, so you need to understand the interplay of all the three topics. Very, very important for you to understand. So let me summarize this by making a statement. And probably, okay, there is no space in the next one, so I'm going to put it here. Bear me out on that one. Covariance is to a matrix what correlation is to a data set. So in the world of data set that we deal with for machine learning, what have you, we call that as correlation. In the world of matrices, we predominantly use covariance. Okay, in the world of data sets, for data analytics, we use correlations. So covariance is to a matrix what correlation is to a data set. I just wanted to keep that in mind. Otherwise, your correlation is a dimensionless version of your covariance. And more generalized idea of a covariance in a setting where you're looking at the covariance of a variable against itself is the notion of variance of that variable itself that we're talking. And variance is always one-dimensional, whereas covariance is for two variables, two random variables, if you will. So whenever you take the covariance and divide it by the standard deviation of both the variables as a product, what you get is the correlation. And the value lies between -1 and +1, which tells a lot just about the direction of the relationship and, more importantly, the strength of relationship. Okay, so what I'm going to do, I think we have covered enough theory. We talked about the definitions, we understood the formulae, we understood how the interplay of one with the other is, and therefore we can transition into seeing demo. Okay, so to that extent, I'm going to go to this slide. I shall draw the covariance formula here one more time just to make sure it will bring that required attention to this slide for interpretation. So I is equal to 1 to n xi minus x bar yi minus y bar. Okay, so what you see here is a data set, or if you think of this as a matrix, it's fine. So I've called this first column as subjects, or number of records, if you will. So the n in this case is equal to 4. So n is equal to 4. So that's what you're seeing here. So n minus 1 would make it 3 because it's a sample. X, y, and z are 3 random variables. This is a matrix that I have where each of those variables have taken certain values. Like for example, x for each of the subjects of the records as the observation of the values recorded as 2, y 5, 4, 6, 8, z 4, 1, 4, 6. Okay. So what I've done is to look at the calculation of the mean for each of those variables. The average value of x is 2, average value of y is 5.75, average value of z is 3.75. I'm going to look at and explain in Excel in a bit for this demo, but allow me to explain these two tables quickly. So here what you see, for several combination of the variables like x with y, x with z, y with z, etc., we could come up with covariance. So therefore, I've got covariance of x and y. Notice, I already mentioned, let's go back to that slide. I think somewhere I mentioned it. Covariance of xy is same as the covariance of yx. So therefore, in the last slide that you see here, covariance of xy is equal to covariance of yx. This is equal to this value. How did we compute? I'll just show it to you in a bit. Similarly, covariance of xz can be treated as equivalent of covariance of zx, and we can see how the computation goes. And the last combination is xy, xz, and you can think of it as yz, and the reverse is also true. Yx, zy, zx, all of them are true. On top of it, we need variance. So what is variance? A generalized idea of a covariance in a setting where you're looking at covariance of a variable against itself. So we can think of covariance of x with x, y and y, covariance of z and z as the variance. Okay, this gives me the variance. Okay, how did I arrive at these values and how did I actually populate this table is a matter of detailing, which I can transition now to Excel to elaborate this further. Okay, so let us go to Excel and see how all these things come into being. Hope all of you can see the Excel sheet is shared. So what I explained in the slides, I think it's going to be useful when I explain it using Excel, because I've also keyed in the formula here. So this is the data set that we talked about, and these are the respective mean values for each of those variables x, y, and z. So here we're calculating the covariance of xy. One more time, please note, covariance of xy is same as the covariance of yx. So this is the formula. Covariance, this is used as a sample, is taken this values here for x along with the values here for y. Probably I can show you this quickly in Excel. So go ahead and type with equal to sign. That's how you invoke any Excel function. Okay. Select these x values here, x column rather, comma, and select the y because we're looking at the covariance of x and y. Close the parenthesis and say enter. You will get the values. So notice here, covariance of x and y is 0. Therefore, covariance of y and x would also be 0. Similarly, I've calculated the covariance of x with z, other combinations x and z. And we have calculated for y and z. Turns out, for covariance of y and z is 3.250. Okay, so it need not be these values. You can change these values for playing around. Once you go through this video and absorb the content, then you can play around. That's our playground for you to practice. So this gives me the covariance values. How do we populate this variance covariance matrix? We'll just talk in a bit. So let's go to the second or the last table here, third table, in terms of the calculations here. You can see it as the last table here. So covariance of x with x itself, that's nothing but your variance. Okay, so how do we calculate? Similar to how we did in the above table, we're taking this time covariance of x with x. So it is these values with these values itself, isn't it? It's a no-brainer. So it turns out covariance of xx, which is nothing but the variance of x, will be 0. So I'm going to call it out here if you want. This is variance of x. So this is variance of y. And this is variance of z. Okay. So it turns out covariance of y and y, and therefore the variance of variable y is 2.917. This is the formula applied. And the variance of variable z is 4.250. So this is the important matrix. Okay, so all this heavy duty that we did is to go about populating this. Okay, I've already created some placeholders in terms of highlighting with different colors. You can see the diagonal elements of this matrix is highlighted in yellow and off diagonal elements are highlighted in blue color. So covariance of x with y, so it is x here and y here. So this is the cell which captures the value for covariance of x with y. Okay, I'm going to populate. So I can say equal to here and then click on this value and say enter. So covariance of x with y is 0. Similarly, we have covariance of x with z. So I can populate here equal to, and xz is this value, which is nothing but E14. Yes, you can populate this. There is something interesting about variance covariance matrix that you should be knowing. I'll just come to that in a bit. We'll also look at covariance of y with z. Covariance of y with z is 0.250. So I click on this cell, click equal to, and then click on this value and say enter 3.250. Yes, let's go back to that point. There is something interesting about variance covariance matrix. It will always be symmetrical about the diagonal. That essentially means you see covariance of xy is 0, therefore covariance of yx is also 0. So I can simply go ahead and take coefficient of yx also to be 0 because I know it is symmetrical. zx would also be 0. So I can take this and put it here. Because of symmetry, I can go ahead and take this value here. So notice here, if you look at the off-diagonal elements, the ones that is highlighted in blue color, please feel free to refer one off of the diagonal elements because they're symmetrical any which way about the diagonal. Okay, in a larger variance covariance matrix, you will get confused if you look at both. Look at one side because this is the exact replica or the mirror image of the other. I usually prefer to see the lower of the diagonal elements just for convenience. There is nothing else. Okay, so here this is 0, this is 0, this is 0, this is 0, this is 3.25 and this is 3.25. Goes to establish the fact that variance covariance matrix is symmetrical about the diagonal. So the off-diagonal elements, just to conclude on the covariance part of it, the off-diagonal elements in this variance covariance matrix is the values representing the covariance. Now we need to populate the diagonal elements. So what is this diagonal elements? As you can see, covariance of variable x with itself is a generalized idea of variance. Okay, variance of a variable with itself. Covariance of a variable with x with itself is variance of x. So this is variance of x. So this is variance of x is this value. So for the variance of y, I'm going to select this value, and therefore last but not the least, for variance of z, I'm going to select this value. So the diagonal elements in a variance covariance matrix will always be representing the variance. The off-diagonal elements in a variance covariance matrix will always be representing covariance. Okay, since I talked about something like this, I made a statement. Covariance is to a matrix and correlation is to the data set. If it were a data set and if you're using correlation matrix, something here to think about, okay, not to get confused though. Correlation of variable with itself will always be 100%. Do you remember? Which is more prevalent in a particular class of data. Time series we look at and we talk more about autocorrelations there. Okay, don't get confused. So in conclusion, variance covariance matrix is an important artifact of this video today. And one more time, can I remind you or request you to go back to part 1 of this series because that's important. In part 1, we covered matrices, we talked about linear transformation, we talked about eigenvectors, and we talked about eigenvalues. Today, we talked about variance covariance matrix in this video. So bring them all together. Make no mistake. You have a very solid foundation of mathematics behind principal component analysis. In the subsequent videos, I shall talk about singular value decomposition, and in further videos, I shall bring all of them together to go from end to end, demonstrating, let's say in Python environment. If you want R environment to be done, also let me know. I'm comfortable to do in both the environments. End-to-end perspective of bringing this understanding to extract uncorrelated dimensions, if you will, as part of unsupervised learning technique like principal component analysis. So that will be the end-to-end perspective of the application of these techniques. How whatever we have learned in these 2 videos and probably one more video I have to create for some more content for mathematics of PCA, particularly single value decomposition and the like. These things come into play a lot when you are looking at applying principal component analysis. I think with that I'm going to stop in this video, but not before I thank you, and I must congratulate if you have made this far in the video and in this journey together. Congratulations to each and everyone. If you have liked what you saw, please give it a like, please upvote it, subscribe if not already, share it with your network, and of course please enable the notifications not to miss the upcoming videos. Okay, So as always, it's a pleasure sharing my limited understanding of the space. Thank you. This is Manjunath signing off. I'll talk to you in my next video. Bye-bye. Take care and happy learning.